This LETI webinar on operational carbon in whole life carbon assessment. We are just waiting for people to log in, and then we will make a start in 1 minute's time. So hello and welcome to this LETI webinar on operational carbon in whole life carbon assessments. So we will now make a start. So let's start the webinar. My name is Michela Ravaglia, and together with Clara Beckner-George and Alex Johnston, we have been co-leading this LETI workstream. This webinar is a part of a series of talks that LETI are producing over the first half of this year on different aspects of whole life carbon, reflecting the work that LETI have done to date, but also a number of publications coming up. This includes operational energy modeling guidance, demolition and retrofit, embodied carbon specification and procurement, circular economy, energy from waste, and much more. The webinars are taking place every 2 to 3 weeks on Tuesday lunchtime, and details will be published on the LETI website, leti.uk, where you can sign up for upcoming events. Please note that all seminars will be recorded and made available on the LETI website. We are really excited to share with you that yesterday, LETI has launched the opinion piece on operational carbon in whole life carbon assessments, which is the topic of this webinar and the result of the work of over 60 LETI volunteers over the last year and a half. You can now download it for free from the LETI website. Look out for the link in the chat. We are really keen that you are out to spread the word about this opinion piece and webinar. So please spread the word on social media throughout the presentation, but also afterwards. So this is the agenda for today's webinar. After a short introduction to LETI and their work, Clara will cover an introduction to whole life carbon assessment, the reason for combining targets, and the workstream conclusion. This will be followed by Alex explaining the selected methodology and Clara illustrating how results are graphically presented. I will then run through all methodology explored by this workstream with Leighton Smith and Barney Evans introducing an upcoming publication. Alex will explore some case studies and explain their outcomes. And the final reminder of the workstream recommendation will be followed by Q&A session. So please type your question as we go along in the Q&A box, not in the chat, otherwise we won't be able to see them. Please like other people's questions so that we can prioritize the most voted. If you're not familiar with LETI, LETI is a voluntary network of over 1,000 built environment professionals working together to put the UK and the planet on the path to a zero carbon future. Established in 2017, it comprises of a large group of volunteers working across a variety of areas within the built environment. In 2019, LETI set out to create guidance that would enable the industry to design and deliver low carbon homes that were aligned with the 1.5 degrees Celsius pathway. Recognizing that for too many people within the industry, this was a significant leap in knowledge, they wanted to make it as accessible as possible. This guide sets out processes, limits, and strategies for minimizing the carbon emission associated with the most common typologies of building in the UK. And a testament of its success is that it has now been downloaded over 100,000 times in over 100 countries. The Climate Emergency Design Guide has been followed by several publications that are available to download through the LETI website, which include guidance on embodied carbon, limits alignment, whole life carbon, retrofit, circular economy, case studies, and much more. We will shortly add the link in the chat. I will now hand it over to Clara for the Whole Life Carbon introduction. Thank you, Clara.
Hello, everybody, and thanks for joining us today, and thanks for the introduction, Michaela. So we all know that we need to reduce carbon emissions of our built environment to be aligned with our climate targets, right? And this means we need to reduce the whole life carbon of new buildings and existing buildings. And the carbon emissions, or the technical term is the whole life carbon emissions of a building, which contain both operational carbon and embodied carbon. Operational carbon are the carbon emissions associated with operational energy that we use to heat our buildings, provide domestic hot water, provide cooling, lighting, pumps, fans, plug loads. And embodied carbon is the carbon emissions associated with materials and construction processes throughout the whole life cycle of an asset, which excludes the extraction of the raw materials, the transport, the construction, the maintenance, replacement, and the end of life disposal. So when we use the terminology upfront emissions, or the A1 to A5 emissions, so emissions up to practical completion, and life cycle embodied carbon emissions, looking at including in addition the embodied carbon with replacement and maintenance in use and end of life. So traditionally, the focus has been on reducing operational carbon in our industry, right? And this is because we burn gas and oil to heat our homes and our buildings and provide hot water to us. And this creates a lot of carbon emissions. And also we've got kind of poorly insulated buildings. So if you look at the graph, you can see that for medium-rise residential, even for a building that is compliant with current regulations, most of the carbon is operational carbon, with a smaller proportion relating to embodied. And that's why the industry hasn't focused so much on embodied. But embodied carbon has always been produced every time we use a material and when we build buildings, but it was often forgotten or not really understood. Now, when a building doesn't burn gas, when it uses just electricity, and with the projected decarbonisation of our electricity grid and our efficient buildings, you can see that our operational carbon really reduces. And that means that even if you have the same amount of embodied carbon, it massively increases in proportion, right? And that's why over the last 4 years, there's been an increasing discussion in embodied carbon, and it's being talked about even more and more in design teams and with developers. So as you've joined this webinar session today, I imagine that you've engaged in whole life carbon. That's why you're here, you're interested. You might have even read our embodied carbon primer we released in 2020, or our handy one-pagers in embodied carbon and whole life. It might be that you followed our carbon alignment process in 2021 and have engaged in our embodied carbon limits that we've been developing with Whole Life Carbon Network, RIBA and ISTRAT, which give kind of banding for embodied carbon of 4 different archetypes, with a kind of current best practice of a C pushing towards a B rating. And over time, we need to try and improve on that. It may be that you've even used our reporting templates that we developed to easily understand how we're doing in terms of the embodied carbon of buildings and what elements we're including. Or even you might have been shown, one of your projects might be shown in our embodied carbon case studies. So if you hadn't had a look at these, do download them from the website, and also check out the previous session, webinar session 2, to find out more about this. Right. Maybe you're here, but your focus hasn't been on operational carbon, on embodied carbon. Your focus might have been on operational carbon. You may have been modelling the energy consumption of your designs, or metering energy from buildings, really engaging in the topic of reducing operational energy, so that you can work out how to best reduce carbon emissions. So I'm sure that you will have some context, and maybe this introduction wasn't necessarily for you, but it's always really good to make sure that everybody's on the same page and it's clear that the terminology that we're using. So we've talked about whole life carbon and embodied carbon and operational carbon. Now, I think there's one last piece that is important to introduce, and that's the concept of kind of LETI EUI limits. So in order to be net zero, we need to make sure that all the energy over the course of the year can be produced by on-site renewables or off-site using the UK's renewable capacity. It's kind of pretty simple, but you'll probably be familiar with these graphics. We've been showing them quite a while at LETI. But the problem is we need the whole of the UK's buildings to be net zero, right? And in order for that to be the case, we need to make sure that there is an equitable distribution of the renewable electricity that we have. We need to make sure our buildings aren't exceeding that. Otherwise, not our whole built environment will be able to decarbonise. That's why in 2020, LETI developed these EUI. We called them EUI targets at the time. As you may be aware, we're trying to change the terminology to limits because actually it's a maximum, a limit, not a target. So we developed these energy limits for residential, office and schools, and they've been implemented in a lot of projects, and I'm sure that you're aware of these. But just in case you aren't, the energy use intensity includes all energy uses, regulated and unregulated, and you divide that by the floor area. It does the bit that it doesn't include is anything relating to electric vehicle charging, so that's not included. And whether you have PV panels on your roof or not on your roof, it doesn't affect your energy use target, your energy use limit. It's not included in the calculation. So you need to achieve a certain energy efficiency of your building, regardless of whether you have on-site PV or not. Hopefully that's cleared things up a bit. So let's get back to the basics. Operational carbon plus embodied is whole life carbon. So you'd think it'd be pretty simple, right? You think, okay, well, we know how to calculate operational carbon and embodied carbon. You add them together, and then you get a result. And I just shared a few of them in my intro slides, actually. But depending on the assumptions of whole life carbon, the results can look very different. You can see here, this is the same building using the same data, and it's got very different amounts of whole life carbon, right? And that's primarily because of the treatment of how you translate operational energy into operational carbon, right? And that is the focus of this work stream, as Michaela is saying, operational carbon in whole life carbon assessments. It's quite a niche topic, but it actually really does, it fundamentally affects a lot that we're doing in the built environment today, which is why we've. So, depending on the assumptions that you use, as I said, then the operational carbon has a different size, and that really affects these proportions. So let's outline the problem in a bit more detail. So this diagram seeks to explain it a little bit. So the first thing is that often compliance modelling is used. Now, the purpose of modelling to do with Part L regulations isn't actually to predict energy use, and it often underestimates energy consumption. And therefore that starting point of kilowatt hours can be not correct, which is not very helpful. Secondly, in current rules of whole life carbon assessments, the future embodied carbon that you emit through the maintenance and replacement cycle far in the future doesn't have decarbonisation of factors on it, and that means that it actually would be smaller than we think in reality. And so that's slightly confusing because you normally have a decarbonised operational energy but not a decarbonised embodied carbon. So that's a bit tricky. Often the embodied carbon of the energy infrastructure itself isn't included. And that means you're not fully understanding that if you're using a certain amount of operational energy, you're not including that additional embodied carbon that's associated with building new power stations and upgrading transformers. So that's the difficulties with the current approach, and that was really the starting point of our work stream, and we tried to find solutions that met this. So let's get back to the basics. So we need to really understand this operational carbon piece, and to calculate operational carbon, it's just you times operational energy by energy carbon factor. So we're going to be talking a lot about carbon factors. Hopefully you like that. And fundamentally, you just times operational energy by your energy carbon factor, and that's your operational carbon. And then your embodied carbon is your upfront carbon plus your in-use stage B carbon plus your end of life. And these last pieces, you need to apply an embodied carbon decarbonisation factor to account for material decarbonisation. So that's kind of simple enough. But here where the tricky thing lies, there's a lot of interrelationships between these items of the equation. If you were to kind of do that on an Excel spreadsheet, I've forgotten what it's called, but when it can't calculate it because they're all dependent on one another, that's kind of what happens really. So, you know, the grid, the energy carbon factor itself needs to include the embodied carbon of the energy infrastructure, but it doesn't. The grid decarbonisation assumptions in the energy carbon factor actually are affected by how much energy the building or all the buildings in the UK are using, because there's this finite renewable capacity. And there are various bits of uncertainty. So at the design stage, the operational energy is predicted by an energy model. But how closely that energy model and energy consumption is in reality depends on how the building is occupied. And fundamentally, you can meter this though, so you can understand the operational energy in use. And there's a bit of a feedback loop, which is good. But for embodied carbon, it depends on the procurement of the materials, as well as the actual lifespan of the building, and the maintenance and replacement rates. So there's uncertainty there. And you do a post-completion life cycle assessment to understand the embodied carbon, but it's hard to actually have a more of a feedback loop because it's still based on an energy model. So how do we know what the right method is and how to solve the problem? This is where we started as the work stream. And firstly, before thinking about that, you need to work out, so what is the actual purpose of carrying out this whole life carbon assessment? Because there's loads of reasons why you do it. You might do it for helping to inform design decisions at an early stage. So, do we add this extra pane of glass? What about mechanical ventilation? What about a different layer of insulation? What about the MEP systems? You might do it to compare the whole life carbon of different projects, or rate projects against the benchmark. Maybe as a developer, you want to understand the whole life carbon of all of your different projects you've got in your pipeline, or also as an architecture practice or an engineering practice, you might like to do the same. Another reason would be to predict the whole life carbon of an asset, so you can understand perhaps the likely carbon offsetting costs, or you might be just doing a post-completion embodied carbon assessment. And lastly, it might be to do with annual reporting, so just what whole life carbon of the building used or emitted in the last year. Wide variety of reasons, and actually kind of think back to the interrelationships, depending on what the purpose is, that you actually kind of potentially different assumptions can be used. So we thought we'd just stick to the first one as a work stream because we felt like we had our work cut out already. So we're just focusing on making design decisions. That's it, right? And so when we talk about the methods and why you've chosen them, just always look through the lens of what is useful to inform the most useful design decision making. Okay, so that's what we're trying to address. Okay, I'm going to hand over to Alex.
Thanks, Laura, and great to see lots of people here today for this. So this next section talks through the proposal that the workstream developed. And as Clara said, there are many different relationships between different parts of the whole life carbon equation. And a central part of this is the method that we use to convert operational energy to operational carbon. What is the energy carbon factor that we use and how do we apply it to a project? A key consideration is that the decarbonisation of the grid is dependent on us all collectively reducing energy consumptions in all buildings. There are a series of prediction scenarios that project us towards a net zero grid, but all of these are dependent on us reducing our total energy use, and we need to sort of tie in the total energy we're using with the renewable capacity that's available. So because of this, it's really important that we meet those energy use intensity or EUI limits in order to ensure that we're not using more than our fair share of renewable capacity within an individual project. So this leads us on to the sort of central proposal that the workstream developed, which was a split carbon factor. So, and this is a method that's used to convert electricity consumption in buildings, because that's sort of the more contentious area, to operational carbon. And this method splits the energy consumption below and above the EUI limit and applies a different carbon factor for each of these two portions. So in the bar chart on the left, this shows a building's electricity consumption, a sort of building that just uses electricity. And this building you can see is kind of quite close to achieving a LETI EUI, but there is a portion of energy use above that EUI limit. So the energy use up to the EUI is shown in green, and the proportion above the EUI limit is shown in red. For the electricity consumption up to the EUI target, a decarbonised grid factor is used, as this is the energy that represents an equitable share of a future decarbonised grid. From this, we get the operational carbon that's associated with this portion of the building's energy use. For the electricity consumption above the EUI limit, a non-decarbonised grid factor is used, using a current carbon grid factor. And from this second calculation, we get the operational carbon associated with this portion of the total energy use. And together, these combine to form the operational carbon associated with the project. However, this split carbon factor forms a key part of the methodology. And it's important because it answers a sort of question of how we convert the electricity consumption to operational carbon. However, there is a sort of series of other considerations that must be taken into account when we carry out this analysis. Firstly, it's really important that we use performance energy modelling, because in order to translate this figure accurately, we need to have accurate data on how much energy our buildings are actually going to use. And LETI are currently producing a guide on performance energy modelling to provide further information on this topic. Secondly, it's important that the in-use embodied carbon decarbonises alongside. As we're using grid decarbonisation for energy use, it's only fair that we take the same approach with the materials that are installed later on in the building's life cycle in 20 or 30 years' time. In addition, that there's an allowance for the inclusion of embodied carbon of energy infrastructure, that uncertainty is represented through showing bookends that illustrate a non-decarbonised and a fully decarbonised grid, which we'll talk about in a bit more in a second, and that the first 20 years of operational carbon is shown separately, as there's greater certainty over that portion, and it's therefore more important. And so to capture these considerations, we've developed a proposed dashboard format to present these results, which Clara will talk you through now.
Thanks, Alex. So we're now going to show you what this means in practice, what kind of information you'll be getting as a developer or as a design team to help you make decisions about different options in the design stage. So you can see here, this example looks at the 3 different options, and it shows you the whole life carbon of those different options using the split carbon factor that Alex has just described. So you can see that the upfront embodied carbon is shown in a dark pink, and then the in-use and end of life is shown separately in a light pink, and we've applied decarbonisation to those. Now, our operational carbon, we've actually also split this up into the first 20 years and the remaining 40 years. Now, the reason why we've done this is because of uncertainty. So we're more certain about the operational carbon of the first 20 years than the last 40 years. In a similar way, we're more certain about the upfront carbon as we are the in-use and end-of-life carbon. And so this really helps your brain understand what bits are more certain, what bits are less certain, and that can help in terms of trying to make the right decisions. And we've included the embodied carbon of energy. So as well as that, so we have our split carbon factor as our central methodology to make design decisions on. But because there's so much uncertainty with grid decarbonisation, and because depending on how the grid decarbonizes might actually affect what design solutions are the lowest whole life carbon, because that really affects the interrelationship between embodied and operational carbon. The uncertainty sub-work stream really suggested, and the wider work stream agreed, that we should show these bookends as part of this dashboard. So you can use these bookends to really understand, okay, if the grid doesn't decarbonize, what's the whole life carbon? And what if all the grid fully decarbonizes, so there's no worry about finite source of renewables, so any building can use as much energy as possible as they want, and our grid will still decarbonize. And so you can see here, you can start to see, it's quite interesting, but option 2 is kind of always is lowest in the split carbon factor and lowest with no decarbonization, but it's very similar. It flattens out. Often when you go full decarbonization, it just flattens out the options. So this method's really good at evaluating. It's really useful when your design options have different operational energy consumptions, right? If they have the same and you're not evaluating something that has a change in operational energy, then I would not use this method because it won't help you at all. So it's really good at evaluating different heating and hot water system options and different ventilation options, and also evaluating different building scenarios. So what I meant to mention here is that LETI are developing an Excel-based tool, which means that you can put in some simple pieces of information like operational energy and your embodied carbon, and you'll automatically get this dashboard output. So all the factors will be automatically applied, which means that hopefully that's useful in the industry. We can get used to that kind of standard way of reporting, so we can easily and quickly do these whole life carbon assessments to inform design decisions. I'm now going to hand over to Michaela to talk through our methodology that we went about as a work stream to come up with this conclusion.
Thank you, Clara. So moving on to the next, thank you. In order to frame this work stream, we need to take a step back and look at previous work carried out by LETI. So in December 2020, LETI published an opinion piece entitled Whole Life Carbon, Separate or Combined Targets. A consultation was then carried out between the end of 2020 and the beginning of 21, asking consultees to read the opinion piece and respond to one question. When reporting on whole life carbon, the operational energy consumption must be multiplied by a carbon factor to understand the carbon emissions. The consultees were asked to select one of the proposed carbon factor options presented in an opinion piece. The consultation resulted in a lack of consensus or clarity, and the conclusion was to set up this workstream to further explore the issue. Just a reminder of what we are trying to achieve, combining operational and embodied carbon to help making design decisions. So we need to understand how to translate operational energy into carbon. And therefore, we are trying to determine what energy carbon factor we need to use. So let's start with a brief introduction to the process followed by this work stream. First, the group reviewed the previous work that LETI had undertaken on this topic, and then started to explore and discuss a vast number of methods of converting operational energy into carbon. Next, these methods were grouped together under main methods explored, and a series of voting was carried out to select the methods the group wished to explore. A number of criteria were kept in mind when considering potential carbon conversion methodology. Is it easy to implement? It can be amended and adapted when carbon related to electricity grid projections are updated. It is based on a publicly available, regularly updated dataset. It drives the right outcomes. It doesn't create a perceived performance gap. It can be applied to all building types, and it can be applied to different case scenarios. This resulted in the 6 sub-work streams shown in this table. We will briefly go through them one by one. The group was split in subgroups, one for each sub-work stream, and developed the methodology further, exploring their advantages and disadvantages and refining assumptions. So the first one is method A. investigated the total annual approach, where either a single factor is applied to the energy consumption that represent an average of forecast carbon factors for the time period, or annual factors from a forecast are applied to the annual energy uses projected in each year. I will then hand it over to Barney Evans and Leighton Smith that will give us an overview of Method B.
Thanks, Michaela. So I'm Leighton and I'm with Barney. We're members of Workstream B, who worked on an hourly approach to operational carbon assessment. And we're developing this into a separate LETI opinion piece and a proposed methodology. And it's going to be titled Time and Use, the Missing Dimension in Operational Carbon. So just to give you a very quick breakdown of what this will be. Fundamentally, why do we think hourly carbon factors could be an approach? Buildings are being designed via an electric strategy, accounting for increasing renewable energy and taking advantage of a decarbonised grid. So currently we use an annual emission carbon factor, and we understand that this hides a variation through the average. And electric grid intensity actually varies by hour, by day, by season. And this is a function of renewable energy, but also demands across the grid. So this graph effectively summarizes the point we're making, which is effectively there's a daily variation in carbon factor, which is not being taken into account via an average. An average would just be a static across this whole day in this example, but also the whole year. So the use of this static emission factor misses the benefit of using carbon, electricity and associated carbon at certain times. So when there's more renewable energy on the grid, utilizing or using energy when there's a surplus of renewable energy would result in a lower carbon functional use of a building at that time. And also it perversely disincentivizes energy storage and demand side response measures in terms of embodied carbon as a function of whole life carbon assessment. So currently we can't take an advantage of the benefit in a reduction or saving in operational carbon due to energy storage, but we do get the penalty of additional embodied carbon. So we think that we're failing to represent reality in a design stage assessment, and so we think that we can broaden the approach, and members of Workstream B will publish this separate opinion piece and draft methodology, so look out for that soon. Barney, so I get everything?
Yeah, I think so. Later, I just had, this graph is a really good simplification of our annual variation in grid emission factors, but it really understates it. The grid emission factor can vary 3- or 4-fold, so it can be a huge difference. And the fundamental point, as Leighton said, if we don't recognise the benefit of energy storage and charging your car at different times, then we'll massively hold back the grid decarbonising, because that's becoming more intermittent and needs more balancing support. But so yeah, coming soon.
Cheers. Hand it back over to Michaela.
Thank you both. So looking at the next method, method C, is this split carbon factor that has been recommended as the main outcome of this workstream, where a carbon factor is applied to electricity consumption that meets LETI EUI targets, with higher carbon factor applied to electricity consumption higher than the LETI EUI targets. Method D proposes to use a different carbon factor that depends on if the building will use renewable energy or not. Method E considers an approach that includes the embodied carbon of energy infrastructure. And finally, F is the overarching modeling uncertainty that is applicable to all methods. This subgroup explores uncertainty around the whole life carbon modeling and how to acknowledge this. This group proposed uncertainty bookends that illustrate the scenario of non-decarbonization or full decarbonization of the grid. and which also form part of the workstream recommendation. And to close, before moving on to case studies, we will have a brief overview of benefits and disadvantages of all the methods explored. Just a reminder that the workstream recommendation is to use method C, the split carbon factor, bookended by decarbonized and non-decarbonized grid as per workstream F, uncertainty modeling, which decarbonized scenario is obtained by using method A, the annual total approach, and included the impact of embodied carbon of energy infrastructure as per method E. The two methods that have not been included in the recommendation are B, which will be developed as a separate workstream, as Leighton and Barney just explained, and method D, renewable procurement, as it is not relevant to design stage. With the exclusion of method E, no other method considered embodied carbon of energy infrastructure. Method A is simple and quick and only requires annual energy data, but on the flip side, it doesn't incentivize low energy use intensity buildings. Method B is being explored separately for the opportunity it offers to design and manage buildings that shift demand to period of low carbon intensity and produce a closer estimate of real carbon emissions at design stage. Adversely, it requires hourly projection of the grid over a 60-year period, which might be difficult to estimate and does not account for regional factors. Method D incentivizes investment into renewable energy through green tariff PPAs, but adversely, it does not incentivize low energy buildings or investment on-site renewable. And finally, method E, with better exploring the impact of whole life carbon emission relating to module P6 energy use. As current data presents a range of values, this might lead to different outcomes. I will now hand it over to Alex for the case studies.
Thanks, Michaela. This next section explains how we use case studies submitted by the workstream to test these different methodologies. So as described earlier, we're at a point where we had a series of methods, but we needed to be able to test them to see what the results were, and also, I guess, if it actually made a difference, which option we used. Out of the workstream methodologies, we tested all of the approaches except the two shown in grey, as we've discussed. So the hourly approach, there's sort of partly a lack of available data, but it's also becoming a sort of separate workstream. And renewable procurement, because this was more about carbon accounting rather than design decisions, which was the focus of the workstream. So these are the case studies that we tested listed by type. And what we were looking for was case studies where there were design decisions which explored potential trade-offs between embodied and operational carbon. So there were some fabric examples of, so there might be more material and therefore more embodied carbon in insulation, say, but the energy use is lower. So it sort of creates perhaps an interesting sort of potential trade-off. And also systems options where you could have a more efficient piece of mechanical equipment that would reduce the energy use in the building, but this could potentially be made of more material with a higher embodied carbon value. So again, a point at which there could be sort of trade-off that would be interesting to test these different outcomes. And another sort of key question that we asked ourselves is, what are the case studies trying to assess? And the sort of two things that we asked were, did it affect which was the lowest carbon option? And also where what we described as sort of magnitude of change was different. So results that might appear kind of quite different using one option and quite similar using another. And there are a couple of examples, and the sort of table is just describing where we felt these things were affected. And so probably about half of the case studies, the lowest carbon option was different, and about half there was a difference in this magnitude of change. So yeah, there was some cases where it was affected and some where it wasn't. So this first case study illustrates where there was a difference in the lowest carbon option. And this was a case study that looked at communal heat pump or ambient loop options for a new build residential scheme. And in this case, depending on whether you use method A or C, this would affect the option that you'd choose. And there's just a zoom in on that on the next slide. Thanks, Cara. So yeah, with method A, you would choose option 1, and with method C, you choose option 2. And then the second is a case study that illustrates this difference in magnitude of change. This case study looked at comparing a couple of options for heat networks and a couple of options for individual heat pumps. And in this option, using method A, option 1 was a little better, but probably fairly similar to option 4. So that's probably a bit of analysis that would tell you it doesn't matter so much, and other factors might come into play, like cost, buildability, or whatever the project specific constraints are. But with method C, option 1 is sort of clearly by far the best. In fact, option 4 is now almost the worst. And what these case studies showed was that both of them show that the choice of method does indeed matter, and that the design decisions would change based on the calculation you use. However, that's not to say that there weren't some case studies where all of the options gave the same conclusion. An example of this was a case study that looked at iterative options for a new build semi-detached house. And I think what this shows is that whilst on a very granular level, there may be some complex decisions that you can make where there are trade-offs, there are also fundamentally good iterations for whole life carbon as you progress through a design, and as you move away from a business as usual case to low energy and low embodied carbon designs. And lastly, it's just a bit of a call out. If anyone does have any further case studies, that'd be great to see. We did receive a good number within the work stream, but there weren't lots of examples which had both of those operational and embodied variations. So we're on the lookout for more. So please get in touch if you have a case study that meets these criteria, and you can email us at admin@leti.uk. I'm going to hand back over to Clara.
Thanks, Alex. So having investigated these methods that affected the lowest whole life carbon option, or the order of, or the magnitude of change, in true LETI style, the whole work stream were given the opportunity to vote on what they thought was the most appropriate method or combination of methods. And you can see here, using the pink and red colours, half voted for either the split carbon factor or the embodied carbon infrastructure, or a combination of both. Some members of the work stream voted in blue for sticking with method A, which is similar to the kind of a standard approach that's used in industry. And some you can see in purple thought we should show all the methods. They are all helpful. And then we've got a few in kind of the teal colour that say you shouldn't bring operational and embodied carbon together to make design decisions. And then in the yellow, it's a kind of unsure or another solution. So this is kind of just a bit of a recap about what Michaela and Alex have been saying. You know, we've decided to use method A as part of the annual book, as part of those bookends. And method B is being worked on in more detail. Looking forward to that publication. And you know, method C and E are within our central scenario. D is being discounted because it's not so relevant for design stage assessments, and the recommendations of the uncertainty group about having the bookends and having first 20 years of operational energy separately have been included in that dashboard. So I'll talk about a summary of our recommendations. Now, you know, performance model, energy modelling must be carried out. You can't use, if you're using compliance energy modelling, you can't bring it together with embodied carbon to make whole life carbon design decisions, because you don't know enough. The resolution of that and scrutiny of that operational energy is just not good enough. So you can't use it to affect design decisions. This central split carbon factor method that addresses these interrelated factors that we've been talking about today is our kind of key recommendation. But we have also said that in-use embodied carbon should have a decarbonisation factor, and we need to include the embodied carbon energy infrastructure, and we want to address uncertainty. So, we've talked about, so yeah, here's our proposed reports for, well, I suppose this is our kind of description of our conclusions. And before I hand over to Michaela to lead the Q&A, I guess I just wanted to say, this is quite a technical topic, right? At the beginning, it was very high level, what's whole life carbon, various bits that you probably all heard before. Then we got into the details, and we really had under the hood trying to work through, okay, the details behind a little factor within an equation that has a big impact. And, I'm sorry if it got a bit technical or a bit, difficult to follow at times if this is a subject you're not so literate in. We just really wanted to share with you. I think if you're a LCA professional, whole life carbon specialist, you'll understand these numbers, and it's really kind of, I think the details will be clear. If you're not, we still think it's really important to engage in the details. There are certain equations or methods that really govern how we make design decisions. And if you're around a design table and a specialist says, oh, well, we should do this because of this, we really want to give you the literacy to be able to question that, and to be able, we really think that it's important that design professionals, whatever their role is, actually, when we're affecting whole life carbon, we need to really peel back the layers a bit, as you can see, and understand fundamentally what assumptions are being used to drive these decisions, so that we can make sure that the best decisions are being made, if that makes sense. So this is quite a niche topic in a way, but I'm really glad that you stayed with us for the presentation, and we really hope that you found it interesting. I'm going to hand over to Michaela, and I'm sure we don't have that long for Q&A, but hopefully we'll address some of the important or most voted questions.
Thank you, Clara. And thank you everyone for posting quite a lot of questions, I must say. So we're not going to be able to go through all of them. So we're going to pick the most voted. If we don't have time, we will either get back to you after the webinar, or even consider setting up a further session for Q&A only. So I'm going to start with an easy one that few people have asked for different type of buildings, and is it intention for LETI to advise on operational targets for life science, R&D sectors, or any other sector that is not already included in the ones present on the LETI guidance?
Okay, if I take that one.
Yeah, I think that's definitely one for you, isn't it, with the standard.
So LETI are working with a group of organisations that include UKGBC, RIBI, Strati, REBA, BRE, Carbon Trust, to develop a net zero carbon building standard. And we've been working together for a year now, and we're hoping to, with this kind of big industry initiative that's involved around 300 people in the project team. And as part of that net zero carbon building standard is developing these energy targets for a wide range of sectors. I think there's 14 sectors, and there's 14 sector groups that are right now currently working out the bottom-up performance levels of these different sectors. And within the sectors, there are subsectors. So we really believe that there's quite a few organisations who've been working in the space, creating guidance, RIBA, CIBC, UKGBC, LETI. And rather than us all continuing to create guidance, which is very similar but slightly has something else, sort of slightly phrased differently, we kind of concluding our what net zero carbon is for existing new buildings together as one group. And therefore, these energy use limits will be derived by the net zero carbon.
Thank you, Clara. So another one asked on EUI from Andrew Moore. Should teams be declaring EUI in terms of GIA or NLA or both? Often it gets reported, but it's difficult to see on what basis the figures has been provided on. Also, as the embodied part is typical GIA, how should it be made equitable and transparent?
So GIA, most typical to do it reporting by GIA, but if it isn't, then you need to show it. So you can do like kilowatt hours per meter squared, and you can put an acronym after that. You can say GIA or NLA. At LETI, the homes is by GIA, the schools is by GIA, and the offices limit. We have a GIA limit and an NLA limit because with offices, typically design teams and developers work on NLA.
Thank you, Clara. So Philip Rees is asking one regarding energy use. So you mentioned we all need to reduce energy use to decarbonize the grid. How does this work with adding more capacity, for example, heat pumps, EV, etc.?
Is that something you want to take?
Anyone wants to take this one?
Yeah, I mean, so part of that was something that we tried to address through the workstream E, which is looking at the embodied carbon of energy infrastructure. So that's kind of looking at what the impact of all those things are. I mean, obviously, there's a sort of mass transition to things that have much lower whole life carbon impacts generally, which is good. So it's about kind of trying to make a bit of an allowance for that. And then, you know, the question on sort of heat pumps and plant associated with your building might be one that Clara wants to take.
I think the thing is that because we are having this big switch to electricity, right? The majority of the heat is provided by burning gas right now in the UK, and we need to stop that. And when we stop that, that moves a lot of load onto our electricity grid, and that electricity grid can't get higher, which means we need to reduce the energy in total.
Brilliant, thank you both. So Paul Scannell is asking about early design stages, which is kind of like a fair question because we are looking at taking deciding decision at the beginning of the project. So his question is, carrying out a whole life carbon assessment at stage 1 or 2 is quite difficult. Are there references, guidance, software available for early stages assessments?
Yeah, and there are kind of various tools that will allow you to make kind of predictions early on. And I think part of what the workstream is doing as well is to try and create, you know, it will tell you something about the ballpark you're aiming for. And that's maybe also a question of brief setting early on as well. So, you know, there are, but it is, and it's sort of challenging. It's something that I think a lot of people are learning about as well. I think, you know, if you've done embodied carbon stuff, it seems to go up at every stage. So it's sort of not always the easiest thing to predict early on. But yeah, you know, certainly there are kind of tools and ways of doing earlier stage. And with energy, it's, I mean, I think in some ways it's more about kind of brief and target setting. But you know, similarly, you can start to set parameters early on.
Yeah, and I'd suggest, or I'd recommend that at an early stage, if you don't have to assess the whole life carbon of the whole building, right? And as we've shown that sometimes, you know, you can understand low embodied carbon, you know, make decisions, drive your decision making on low embodied carbon structures and low embodied carbon materials. You don't necessarily need to measure it to know what's low embodied carbon, right? So you can do that for the building, the architecture, and the structure. And then for the operational energy piece, I would say, especially at early stage, if you're using it to inform design decisions, you only need to model the embodied carbon that relates to the bits of operational energy that you're investigating, right? So you could assume a baseline based on a benchmark. So we can assume, okay, roughly this building is going to be 500 kilograms of carbon per meter squared, but I'm going to in detail understand the embodied carbon of a communal heat pump versus an ambient loop. And I'll also do the operational energy piece of that, and then I'll bring them together to understand the whole life carbon of that decision, right? So you don't need to do the whole thing at early stage. You can just do the bits that you're trying to work through.
Thank you. I guess I'm going to go for the last couple quick ones, hopefully, and then we're going to wrap it up. Mindful of time. So Andy Teams asks, how do you include embodied carbon of energy infrastructure?
So you sorry, I'll talk to Alex.
Well, I mean, so it's not something that there's kind of huge amounts of data on, but there are kind of various sources where, you know, there are figures for whole life impacts of different energy, and they vary a bit. And there's also a lot of focus in what they're going to be in the future and their kind of decarbonisation pathway. So within this, we took what we felt was a sensible middle ground. But I think it's an area where there could just be a lot more work done on it, and I think it's something that we need to understand in greater detail. And in some ways, it will probably go one way with decarbonisation of materials, but then probably the resolution of our understanding is quite low. So I imagine there'll be more stuff than we realise. So it's kind of, we'll see where it goes, but it's a good one to sort of have in there.
But the values themselves will be within the Excel tool that we will develop.
Yeah, so watch out for that being published soon. And final one, where does the decarbonized grid factors come from?
They come from the FES, the future energy scenarios. But we're including lots, so we're including the welter tank of the energy generation and the distribution losses, and the welter tank of the distribution losses. So there's 4. It's the FES is for the decarbonised electricity grid, and then we're using the government carbon factors for the welter tank and distribution losses. But that will be all outlined in the tool.
Brilliant. Thank you very much, everyone. I think we need to wrap it up. We are 2 minutes to the close. So thank you all for joining us today, and we hope you enjoyed this webinar. Just a reminder that we are recording this webinar, and this is going to be made available on the LETI website. So if any of your colleagues miss it, they can catch up with it. And now the new dates are being added for the next 3 webinars. So these are the 3 ones coming up. A ticket will be available next week. So do check the website and sign up. And then if you have organized a lunch and learn session and live stream this webinar in your office, please do take a photo and share it on social media and tag us. We would love to see our organization are engaging with this series, and download the opinion piece. So it's been available since yesterday on the LETI website. Share on social media this event so more people can join us for the future ones. So this one was a little bit technical. The others are more less technical. So probably better for a wider audience. Send us feedback. We want to hear from you. So admin@leti.uk. Please do tell us what you think of the webinars. If you have any idea, anything you wish. You can sign up to our mailing list, and so you can hear about the Excel tool being published, but also other events and other updates. Again, just remind you that the call for action from Alex to submit case studies if you have anything that we can assess. So that would be brilliant. And register for next webinars from next week. And check out other LETI publications. So we gave you a little bit of an overview, but there's quite a lot of work that's been done in the past. So a massive thank you to Clara, Alex, Barney, and Leighton for joining us today. And have a great rest of the day.
Thanks all.
Bye.
Yeah.
Bye.
Bye.